What? Oh yeah. It's just the same thing as when you call you on a computer. Yeah, that's what I said. No. It's the same thing as when you call your phone in a computer.
We're gonna do something that's I don't think painful at all, and then I'm gonna do something that's slightly painful, and then I'll tell you I won't do that anymore. So sometimes I think it might be worthwhile to derive formulas. If you want to see all these formulas that we're using derived so that you just know it's not magic, nobody's just making up stuff, and that it's doable, look at the online textbook because I think they derive pretty much everything. I'm just going to take you through a scenario to, let me give you a preview. These are the kinematics formulas you're going to need for the first test. And there's really nothing super mysterious about those. I'm going to write them down in a minute. You can write them down. Again, if you don't like writing any of this stuff, you can just go to my website. I already scanned this. It's there.
Did you go back to that possibly?
Yeah, we're going to get to that.
Oh,
that was the future. Yeah.
That was the first test.
I don't know. Last year it was on, I think I gave a quiz on September 9th. But I don't know if we're going to do a quiz before a test, unless it's just for practice.
I already have a test every day.
You had a test?
We have like a
We're
test.
gonna have
A test or a quiz?
Test.
Really?
Assessment.
Wow.
It's a unit test.
All right. So,
Don't
this,
stress it too much. Now you have another story.
excuse me, if you don't mind me teaching here, I'd like to do that. So we have this deriving a formula for constant acceleration of an object starting from rest. It's a pretty simple situation where something is starting from rest and then accelerating. In this case, it's this nice looking car. And we'll start by filling in some stuff, and then I'll do some algebra, and then I'll tell you that I won't do this a whole lot unless you want me to. So it says, suppose the car moves with constant acceleration. Just about everything we do in here is going to be constant acceleration, including zero acceleration, but we won't have changing acceleration. Starting from rest at the starting line, the car travels from the starting line to the finish in a time of 8 seconds. The distance from the starting line to the finish line is 32 meters. So filling stuff in, guess what x sub 0 is supposed to be? 0 what? Meters. So x is position, x0 is the starting position. And t0 is going to be, now it doesn't have to be 0 seconds, it's probably not. This probably isn't the Big Bang. So, but it's relative to the final time, t, it's going to be 8 seconds earlier. So we can really pick whatever we wanted there. Vx0, the x I will drop a lot, but I think the book uses it to emphasize that when we get into 2D kinematics, we'll have something that will have a horizontal velocity and a vertical velocity. So it'll have a Vy0 and a Vx0, and they won't necessarily be the same thing. So what is V0? If you've been following along, how fast is this car going right now? 0. And now we can do, can't really do average velocity yet, but we can do x. What's x? 32 meters. And t? 8 seconds. And final velocity, any idea? So 4 meters per second is not the final velocity.
That's average.
Yeah, so this, if we want to use the formula, average velocity is change in position over change in time. You don't have to write everything out that I'm writing. 32 meters is delta x. We're going from 0 to 32, divided by 8 seconds, and that gives you 4 meters per second. And I'm curious, last class, this didn't do it for him, but what do you think v is? So the initial velocity is 0. What would the final velocity be? Any guesses? Something reasonable? Okay. So that last class didn't have any idea either, but so that's okay. I'm going to write some stuff on the board here. So just let's just make. I'm going to make up an acceleration, and so here's the car, and it's starting at 0 and it's going this way. And I'll make a table. So this is going to be time in seconds, and this is going to be velocity in meters per second. And I'm just going to make up the acceleration. Let's just say the acceleration is 3 meters per second squared. So as the seconds tick by, 1, 2, 3, 4, 5. I think that's far enough. What are the velocity? Ooh, I forgot 0. Why did I forget 0? It's a messy table now. So the velocity in the beginning is 0. What's the velocity after 1 second? 3. So this acceleration tells you how much velocity you add every second. So 3 meters per second. How fast here? 6. How fast here? 9. And 12. And, oh, yeah, let's 15. I want to go one more second. 18. All right. So this is how the velocity is changing. So from this, by the time the car gets to this point, and it's going pretty fast, it's going 18 meters per second. That's the final velocity. 0 meters per second was the starting velocity. What do you think the average velocity was for this car? 4?
3 meters per second.
3 meters per second? Keep thinking about it. Now there are different ways to get at this. This formula.
I thought it was 8 seconds.
I'm making up a different
Oh, you're
scenario.
doing
We'll go back to that in a second. So one formula is the one we've been using, delta x over delta t. That's one way to get the average velocity, but that doesn't really help here because we don't have a distance. We do have a time. How do you get the average, let's say, of 6 and 10? How do you average two numbers? Add them up and divide by 2. 6 plus 10 over 2, so 16 over 2 would be 8. And so these are all the different velocities this thing has. So what's another way of getting average velocity? You can add all those up and divide by how many there are. What would you get, do you think? There's a quick way. No? Close. What?
Oh, yeah, it's easy.
Oh, so we're gonna have a formula.
So what would the answer be if you took 0 plus 3 plus 6 plus 9 plus 12 plus 15 plus 18 and you divided by 7? 9. So what's an easy way to do it? Where's 9? Do you see 9 up there? Right in the middle.
Immediate.
So how else could you arrive at 9 other than writing them all out and taking the middle one? Sometimes there's not a middle
You can
one.
divide the number of trials there were and then go up to that one.
You could do that. Any other quick way of arriving at 9 there?
Keep saying
Median. That's a hard way though. You have to put it all in the spreadsheet and look for the median. Or list them all out.
the velocity divided by 2. The summation.
What?
Velocity divided by
Which velocity divided by 2?
And
2.
velocity.
So last one.
Yeah. So really if you take the starting velocity and the final velocity
That's right.
and you
I said that.
average, yeah, maybe somebody did. Average those, then you get the answer. So that's a simple way to do it. So when something's accelerating at a constant rate, it's going to add on the same number of meters per second in the first half that it adds on in the second half. So, and it's going to arrive at its average halfway through, time-wise. Spending half the time going slow, half the time going fast, and if you average those together, you're going to get this. The quick way is just to average the first and last. And this could be done in reverse. So let's say we know I'm going to cover that up just to make this really hard. Let's say we know the average velocity is 9. How do you get the final velocity?
Multiply by 2.
Double it, yeah. So this has to be the average of 0 and something. So going back to this example, what's the final velocity here? 8 meters per second. So the average velocity it's going to spend the first half going less than the average velocity. It's going to spend the second half going faster than the average velocity. It's going to reach this at the 4-second mark. So if you just, first half it goes from 0 to 4, it's going to add on the same number of meters per second in the second half, so it's going to be 8 meters per second. 8 meters per second. And now I'm ready to answer the question or solve the problem, what is the acceleration of this car? So we've got enough to figure out delta V. What's delta V?
Change in velocity.
Right, and what would that be? What is the change in velocity? Over the whole thing?
8 meters.
We could look at just the half. Over the whole thing, from there to there, we're adding on 8 meters per second. And change in time? 8 seconds. So the acceleration is,
Meter per second.
yeah, how many meters per second are added per second? I'm just going to write it out like this. 8 meters per second over 8 seconds, we get 1 meter per second squared. So the big leap of faith, the epiphany there, was kind of figuring out that, at least for this situation, the average velocity, if you double it, you get the final velocity. If you don't start out at 0, that's not really the case. But you can always take the starting velocity and the final velocity and average them, and you'll get the average velocity. That's another way of getting them, and that's one of the formulas. So right down here, I'm going to do the same thing except do it algebraically. And I know the order I need to go in, but it might not be automatically apparent to you. So I'm going to write something kind of messy. You don't have to write any of this. I just want to show you that it's just not, it's not magic. So I'm deriving a formula for acceleration that can be used in this situation with any values that you might come up with. So I want to come up with a formula for acceleration that'll work here. I'm going to start out with the acceleration formula.
What is the little bar over the A meaning in?
Average.
Average.
And that'll be left off. I don't know why. People put it on velocity, but they leave it off on acceleration, and then quite often we just leave it off on velocity too. Because you can't really calculate an instantaneous acceleration or velocity. So if I just had this formula, and I gave it to somebody, and I gave them this situation, they wouldn't be able to use it because they don't have delta V yet. So I need delta V. And delta V, I know, is just the, it's going to be V minus V0, which in this case is just equal to the final velocity. But I need that, and that's not really given. So I need to know that in this case, if I do 2 times the average velocity, that'll give me the final velocity. But we're not given the average velocity either, so another thing I'm going to need is the formula for average velocity, which is delta x over delta t. So that's sort of my train of thought thinking. How do I write a formula for this? Well, this is the formula, but I don't know that. I do know this, but that's that. But I don't know this. So now I can put all this together. So if I start out saying that, let's see, V equals, or sorry, average velocity is delta x over delta t. And then I want the final velocity is going to be 2 times the average velocity, so it's going to be 2 delta x over delta t.
You forgot the delta on the first.
Delta, sorry.
Are we supposed to be writing any?
No. I just, like I told you earlier, this is going to be sort of painful, but I just, I don't know. For some reason, something tells me it's worthwhile. And so now if there's the velocity. The velocity is equal to this. I need change in velocity. In this situation, this is the change in velocity. So now I can substitute all this in for delta V. So I can say average velocity equals 2 delta x over delta t. That's my delta V right there. Divided by delta t. and that is 2 delta x over delta t squared. So there's a formula for acceleration anytime you're given a time and a displacement, and you're starting from 0. Only works if you're starting from 0. Hold on just a second, Brendan. And now on the back, there's no formula that's going to look like this that I'll write down and that we'll write down in a minute. The formula that this comes from is actually for displacement, and to rearrange this and get displacement, you've got to isolate that delta x, so we multiply both sides by t squared. T squareds cancel out, divide both sides by 2. These 2's cancel out, and the formula for displacement that you'll see ends up being 1/2 at squared. Only reason I did this is just to show that there's nothing super mysterious and amazingly intelligent about the origin of any of these formulas. The worst one, or I guess the most complicated one, took the formulas that were already there and used the quadratic formula on them. Brennan.
I'm just gonna say, so on that equation where it was average acceleration is equal to 2 times change in x over change in t. Basically, that's just a change in velocity, right?
Right.
That's
Yep.
just, you're just substituting what you
I'm just
saw.
substituting, yep. So I'm doing exactly the same thing we did here, except instead of numbers, which are a lot easier to deal with sometimes, I'm putting in the symbols.
Okay, that makes sense.
Just coming up with a formula that'll always work, which you don't always have to do for yourself because they're often provided.
Is that like a little bit more complicated, I guess?
Yeah, and there are going to be situations later on in the year where you'll be combining a couple of formulas, and it'll be worthwhile to do that kind of thing because you'll realize there's gravity on this side, there's gravity on that side, and it can be canceled out. And if you didn't do the algebra first, then you'd end up going through a lot of extra steps and having extra numbers, which would give you an increased chance of getting it wrong. Here are all the kinematics formulas that you'll need for the first test. And we won't have the first test tomorrow. This isn't AP chemistry. So this one we've been over. Average velocity, what's one formula for average velocity? Delta x over delta t. And a lot of times that's just going to be v equals delta x over t. Or if you see it on the kneecap, actually I've been told we're not taking the kneecap this year. If you're a junior, it's going to be something else. But it's something else. If you were taking the kneecap, they would give you v equals d over t. So that's just kneecap. Now, bless you. The other average velocity formula is what I did over there. You just take the initial velocity and add it to the final velocity, and you divide by 2. So it's really just averaging 2 representative velocities on each end of the event, and that gives you the average velocity. Somewhere in the textbook it says v equals this, which equals that, and last year that messed a whole lot of people up because they were thinking delta x equaled this, and delta t was always 2. I don't know why they would think that. But
What's delta x again? Okay.
change in position, displacement, how far it's moving in which direction. This one we've already been over. Average accelerations, change in velocity over change in time. And now for a new one. This is what I just derived, except this will work for something that's not starting at 0. It's not starting from rest. So it's v0t plus 1/2 at squared. So if you want to know how far something is going, like that car that I was just talking about, you could plug in the initial velocity that, for our example, was 0. That means this isn't going to come into play at all. And then you plug in the time, which in our example was 8 seconds, and the acceleration, oh yeah, which was, no, I didn't give you the acceleration.
What's
Anyway.
VOT again?
I gave you this. So VOT is initial velocity times time. I guess I can write that. Initial velocity.
Time when? Like the
The,
total
it's
time?
like delta T.
Alright.
Change in time.
And yeah, I don't know why it's not never listed as change in time, but this is actually delta T and this is delta T too. Maybe because the deltas just get to be too much. And really this is average acceleration and yeah, but that's the way I'll say the formula. So what that does is, I'm not going to explain what it does. I was just going to explain this difference in the formula from what I just derived. So here's another one. Actually, before I do this one, you can all figure this one out right now. Don't write this down. I'm just going to give you a scenario. Let's say somebody is moving at 10 meters per second. So this is their initial velocity. Their acceleration is 3 meters per second squared. All right? And they're going to spend the next 3 seconds, let me give it a different number, 4 seconds accelerating. So they're starting out at this. That's how fast they're going. Now they're going to accelerate for 4 seconds at this rate. Think about how fast the person's going to be going at the end of those 4 seconds. Are you question or you have the answer?
Oh, I thought it was.
Don't answer it yet. Just hold on. Give people a little time to think about it. Okay, blurt the answer.
Is it 22 meters per second?
22 meters per second. So this is the initial velocity. This is how many meters per second we're adding for every second. This is how many seconds go by. So after the first second, we add on 3. After the second second, we've added on 2. I mean 2 times 3, so 6. Then another 3 gives us 9, and then another, sorry, I'm saying this wrong. After 1 second, we'll add 3. After 2 seconds, we will have added 6. After 3 seconds, we will have added 9. And after 4 seconds, we will have added 12. So 12 plus 10 is 22. If you just thought through it that way, then you derived this formula. The formula for velocity is the initial velocity plus AT. So how fast you're going is equal to how fast you were going plus acceleration times time. Acceleration is how many meters per second you're adding on or taking away every second, and you're multiplying that by the number of seconds. So in this case, I was taking 3 meters per second and multiplying that by 4 seconds because that's how many times I'm going to add on that 3. And I get 12 and add it to what I had to begin with, which was 10.
And that's ending velocity right there?
That's ending velocity. So this is, if you don't see the sub-zero, that means final.
Okay.
And the sub-zero is initial. Thanks for clarifying.
Yeah, no problem.
And then there's one last formula that I used to really not find very useful, but I think it was, I don't know, I just didn't mind using the quadratic formula. You don't really need this formula if you don't mind using quadratic formula all the time. But somebody did the work. They took the existing formulas and they solved for other things. So v squared equals v0 squared plus 2a delta x. So this is displacement. And this is acceleration, initial velocity squared, final velocity squared. You don't really need that, but it's really handy. It saves time. A few notes about this. Make a little box of.
So what's
Help.
the last one? What does that mean?
What does what mean?
What is the last one like? What is it for?
Well, it could be, any of these formulas are for finding any of the things in the formulas. It just depends on what you're given. If you, let's say you're looking for something's velocity. The most straightforward one is, I want to know how fast a car is going. And I've been told how fast it was going at the beginning of some time period. And I've been told the acceleration of the car during that time period. And I've been told how far it's moving and in which direction during the time period. So if you know how far it's moving in which way, and you know how fast it's accelerating, and you know how fast it was going in the beginning, then you can solve for how fast it's going now. Alternatively, if you want to know how fast a car is, how far a car skids, for example. Let's say somebody hits the brakes and there's a cliff up ahead. Are they going to skid off the cliff or not? So you want to find out what the displacement is. You can do that if you're given the acceleration, which would be negative for the car because it's slowing down, and the car's final velocity and the car's starting velocity. So the final velocity in that case would be 0 because you want the car is skidding to a stop, hopefully. The initial velocity is how fast it was going in the first place. The acceleration depends on, well, you'd be given that. And if you have all those numbers, then you can rearrange this to solve for how far it's gonna have to skid to stop. So when you're solving any of these problems, you can solve for anything that's in the equation. You can solve for A, you can solve for T, you can solve for V0, you can solve for delta X, but you need all the other stuff in order to do it. So you need a formula that's got everything in it except for the thing you're looking for. And you don't have to be looking for this thing over here on the left. You can be looking for anything. Make a note that I've already mentioned this, but by convention, rightward and upward, those directions are going to be positive. So if you see a positive value, that means up. It's either going up or it's going to the right. And left and down, those are negative. Any questions? So a lot of formulas there. I'm not going to derive them all. That would just do you in, and me too. This next business, guess method, you don't have to solve problems this way. I listed this out partly because some students struggle with knowing where to begin, and this provides a nice little framework to solve these problems. It's not always going to do it for you, but it's a good way to go about it. I'm also thinking that maybe if you miss a question, I give partial credit. Mr. Chase gives partial credit. And this might give me a good framework for deciding how many points to give you. So the way it works is, first you identify the givens, and what are you given in the question. Then you identify the unknowns that you're looking for. Then find an equation that works for that, that has most of your givens and lists the unknown as well. Then you substitute and then solve. And that's what the guess method stands for. It's an acronym. I'm not going to follow it exactly because I don't really like that, but at least if you don't know where to begin, try the guess method. So we'll do a couple of examples and we'll be done with this. First problem. What's the displacement of a car that starts from rest and accelerates at 6 meters per second for 7 seconds? By the way, your homework is to do these 8 problems. And we're doing 2 examples to get you started. So displacement, that means I'm looking for delta X. And starts from rest. So what is that telling me? What does that give me in terms of these symbols up here? Which one does it tell me? It tells me V0 equals 0. This is the acceleration. And 7 seconds, that's T. So I'm looking for the displacement. I'm looking for something that's going to give me delta X, hopefully in terms of these other things which I have. So you go hunting for a formula. The one that jumps out is this one, because it's the only one that says delta X equals something. But it could have been this one. It could also be this. It doesn't have to be on the left side of the equation. But as it turns out, could we use this one? Do we have time and initial velocity and acceleration? Yeah, so this one's going to work. So I'll write that formula down here. Delta X equals V0T, bless you, or something. If you've been in my class before, you know I've been struggling for years about whether to bless people who cough. I just feel guilty because the sneezing people, they get all this sympathy, and the coughing people, they're probably in more pain. They get nothing.
Yeah.
And really, if you go back to the origin of the blessing people, isn't it to keep demons from getting into them? So my theory is that the people who are coughing, they already have demons, and I'm kind of helping them out by blessing them. I don't know. I don't know if any of that makes sense. So I can just plug and chug from here. Delta x is
Plug
what
and
I'm
chug.
looking for. V0 is 0, so this 0t, I don't really need to put t in there, I might as well, just to make everything really obvious, 7 seconds. That's going to go away. Plus 1/2 times the acceleration, which is 6 meters per second squared, times the time. Don't forget to square it. People forget to square it all the time. And I've done this a few times, so I can tell you that when you multiply this times that times that, yeah, you get 147. What will the units be? Oh, I said 7t, that should be seconds. What should the units be for the answer? Meters. So displacement's almost always going to be meters unless we're working with some other units. If you are familiar with dimensional analysis, when you multiply everything, you should get, if you're not getting the right units in the end, you're probably doing it wrong. Here we've got second squared on the bottom and second squared on the top. Well, denominator, numerator, so the second squared cancel out. One more practice. A nut. I messed this up. It should say a nut is falling or moving, whatever. Falling downward sounds redundant, so I'm going to say moving downward. Or, you know, it might have been even better if I just said falling. No, it's not accelerating. Why not?
Could it be decelerating?
Could be decelerating. But why do I need to change that just based on what else you see there?
Down with that stuff.
Negative, well, why not accelerating?
Because it's a negative.
Well, it's because I gave the rate here of negative 5 meters per second. Is that acceleration?
Oh, it's like going down.
Yeah, so what I was trying to give you here is I was trying to give you the initial velocity of the nut. The nut is falling, and it is going to be accelerating, but right now at this moment in time it's going negative 5 meters per second. Negative means it's moving which way?
Downwards or
Left.
left.
Down or left?
Down. So we're in the up and down dimension. We're not going to do 2 dimensions at once for a while. So this means it's going downward because that's negative. If gravity accelerates the nut at a rate of negative 9 meters per second squared, so why is that negative?
Wait, isn't that 9.8?
Yeah, negative 9.8. I might have said
It's
9.
going down.
Because it's accelerating downward. So it's going downward and accelerating downward. You can be going up and accelerating down, but this isn't. And it's doing that for an additional 6 seconds. There's our time. What will the velocity be? So we're looking for v after those 6 seconds. So we're looking for a formula that's going to give us v, and hopefully it's going to have v0 and t and a in there. Do you see one?
Yeah.
Yeah.
Right here.
So is it saying the initial velocity is negative 5 meters per second?
Yes, that's what it's saying. So, it really, if you just think about it, if you think about, like the scenario I gave you earlier, it's already going negative 5 meters per second, so it's going 5 meters per second downward. The acceleration tells you how much is going to be added on every second. In this case, you're going to start with negative 5, and for 6 consecutive seconds, you're going to subtract negative 8, or 9.8, negative 9.8, minus 9.8, 6 times. That's what the formula is going to do. V equals V0 plus AT. V0 is negative 5 meters per second. And A is negative 9.8 meters per second squared. And T is 6 seconds. And I already did this earlier.
53.8.
Negative 63.8.
Oh, really? I have that written.
And what would the units be? Got to have the units. You always lose a little bit. if you don't. Meters per second. So it's going downward faster than it was going downward before. So
When is the second squared and when is it not squared?
it's squared when it's acceleration, which is meters per second, and it's not squared when it's velocity or time.
Equals.
Why is the negative 5 not how squared then?
Because that was here's the nut. We enter the picture. Our problem, the nut's been falling from the sky, and so it's got a downward velocity. And at the moment when this problem begins, it's going down at 5 meters per second. So its velocity is negative 5 meters per second. And as it keeps falling, it's going to get faster than that, but faster downward. So if I'd made this problem, a nut falls from rest, somebody holds a nut for the sake of physics, and releases the nut, how fast is it going to be going after 6 seconds? We could still use this formula. We would just put in 0 for the initial velocity because it wasn't moving when I let go. And it would be whatever the acceleration is times the time it falls. That would tell us how fast it's going then. But this nut has had a head start. It's already got some downward velocity to begin with. So then we're adding on the new velocity and skating beyond that. Is that?
Yeah.
All right. Okay, so if you go down through these, you'll run into a couple of asterisks. I don't know how hard these is, but these are, sorry. But these is. But I anticipate